Very good morning, class. In the yesterday's video, we have started the topic internal resistance, and I told you that this internal resistance is basically provided by the electrolyte of the cell. Electrolyte of the cell obstruct the path of the charge flowing inside the cell, and hence some potential is dropped inside the cell also. Now today we will discuss what is the value of this internal resistance with respect to the parameters of the electrical circuit like potential difference, resistance and the current. We have already discussed that the internal resistance of the cell depends upon 1. The length of the cell, 2. Inversely proportional to the plate area, and 3rd, it depends upon the concentration of electrolyte also. Okay, so let's start with the internal resistance of the cell. Okay, consider electrical circuit. This is a cell having EMF E, and let this be the internal resistance R of the cell. This is the external circuit, external resistance, R. Okay, now basically when we say cell, the symbol of cell is this, but actually this is an identical symbol, because in this symbol we don't consider the internal resistance, but the practical symbol of the cell is this, because cell also have some amount of internal resistance. We can't make a cell having internal resistance 0, right? There must be internal resistance, because obviously electrolyte always obstruct the path of the charge. So this is basically cell. This complete is a cell. Here. This is your cell. Now let's discuss that current is started flowing from the cell is I. Right? When the current flows I in the circuit, some potential is dropped across the internal resistance, because we have studied in the previous chapter, when current flows through the resistance, some energy got dissipated in the resistor, right? And hence the energy per unit charge will be equals to potential. So here it is, the potential drop across the small resistance is, let's say, V. Now in order to find the terminal potential, what will be the terminal potential? Let us connect a voltmeter across the ends, which will measure the potential difference across these 2 points. Now what will be the total potential? The total potential or terminal potential will be V equals to the EMF provided by the cell is E, but will not get complete E, because some amount of potential is being dropped at the internal resistance R, and the value is basically V. What will be the value of V? The value of V will be current into resistance R, right? This is the drop across the internal resistance. So the terminal potential we get is V equals to E minus IR. So this is the terminal potential across the cell. This expression shows one thing, that if the EMF of cell is, let's say, 5 volt, then if you connect the voltmeter across the terminal, you will not get the value 5 volt. Why? Because some potential is dropped inside the cell. So the terminal potential of the cell is always less than the actual EMF of the cell, right? And it is decreased by the function IR. So this is our first expression to find out the voltage and internal resistance. From here we can find the internal resistance also. What will be the value? Okay, this can be written as IR equals to E minus V also, right? So from here R can be written as E upon V upon I. So this is the value of internal resistance of the cell. In some question we have to find out the value of total current flowing in the circuit. So how can we calculate the total current in the circuit? It's quite easy. Always remember one formula. The total current is basically total EMF divided by total resistance. So by using this formula you can find out the total current in the circuit. What will be the value? Total current I equals to, what is total EMF? So EMF is basically E. It is E, and upon total resistance, the resistance is basically R plus small r. Internal resistance plus external resistance, that is R plus R. So this is the value of the total current flowing through the cell. So please memorize these formulas, is very, very important. Okay. So from this expression, R equals to E minus V upon I. In the circuit, we have an external resistance R. So you know that the potential difference across two parallel components will be same. So if the potential across the cell is V, so obviously the potential across R will also be V, right? So this I can be written as V upon R also, right? Because V equals to IR. Now, if we put the value here of I, R becomes R equals to E minus V upon R, right? So we can further solve it. We get R equals to capital R E upon V minus 1. So this is one more formula of internal resistance in the terms of EMF and potential and the external resistance R. This formula will be used in the one practical examination also. Will conduct the practical in which we find the internal resistance of the cell. So this formula is very, very useful in that experiment. All right. So this is the concept of internal resistance. We have calculated the value of internal resistance also. Now let us discuss these cells. Like when we studied capacitance, we have studied the combination of capacitance, that how can these capacitance can be connected across each other, and then we have studied the combination of resistance also. Now today we will discuss the combinations of cell. How are these cells can be connected in a circuit? Let's start the combination of cells. Combination of cell basically are of three types. First, you all know series combination. In series combination, all the cells are connected like this. Parallel combination. In parallel, cells are connected like this. Then what would be third? The third is mixed combination or mixed grouping. In this we have like this, series also and parallel also. So we will discuss one by one each of the case, series, parallel and mixed grouping, and we'll see what is the total current in this configuration. And when we use these configuration, that means what is the factor which decide that we will use the series combination or mixed grouping or the parallel combinations, right? Let us start with the series combination. Okay. Series grouping. Let's see the electrical circuit first. We have cell and their internal resistance R. And it is connected across an external resistance R. For the ease of calculation, we have taken the EMF of each cell is E, and the internal resistance is also same, that is R. Or we can say that we have connected n number of identical cell in series configuration across the resistance R, right? So you know that when cells or when any potential source connected across parallel, then the voltage across each terminal will be same. But when these sources are connected in series, then their EMF added up, right? So what will be the total EMF in this case? Total EMF, that will be N into E, because we have N number of cell and each cell having EMF E, right? And what will be the total resistance? Total resistance. First, we have external resistance R, and plus we have N number of internal resistance R also. So you know that when we calculate the equal resistance in series, then we directly add them up, R1, R2 plus R plus R3 and all, right? But you know the condition, when all these resistance are identical, then we directly find the equivalent resistance by multiplying the number of resistance into the value of resistance, right? So this will be N into R. All right, so now we have total EMF and total resistance also. Now what can we find? We can find the total current drawn from this system. So we know that total current is nothing but it is total EMF upon total resistance, right? What is the value of total EMF? That is NE. And what is the value of total resistance? That is R plus NR. This is nothing but the total current of the circuit, right? So I equals to NE upon R plus NR. So this is the total current drawn in this series grouping. Now let's consider when this grouping is beneficial to us. What is the condition when we use this grouping? All right, let's see. So I'm rubbing this first. So the current is I equals to N into E upon R plus NR, right? Now consider that the internal resistance of the cell is much larger than the external resistance of cell, right? What I'm taking, the condition is that NR is very greater than the external resistance R, so that we can neglect the value of R. So put this condition in the general equation, you'll get I equals to N into E upon N into R, right? N has been cancelled, so I is equals to E upon R, and E upon R is nothing but it is the current from single cell. So what do you understand by this? It means that if the total internal resistance of the circuit is much greater than the external resistance, then even if you connect thousands of the cell, you will get the current only equal to the current divided by the one cell only. So that means it is of no use. You are connecting thousands of cells, but you are getting the current only equal to the one cell, right? It is clear from this equation mathematically. So this means it's clear that we don't use this configuration when this condition occurs, right? Now let's say what can be second condition. Second condition can be equals to that the external resistance is much greater than the total internal resistance R. So let's just check it out. Okay, so I'm taking that now the second condition is that R is very much greater than R, so that we can neglect the value of total internal resistance, right? Now what can be the current now? Now current will be I equals to N E upon R, right? So here you can see that we are getting current N times of current from the single cell. So if this first one cell is providing current of let's say 2 ampere and you have connected 10 cell in series, so you will get 20 ampere of current. The current becomes N times. So it is clear from this discussion that this grouping or this configuration is used only when the external resistance of the circuit is more than the total internal resistance. Okay, I will discuss the next grouping, next two grouping in the next lecture, in the tomorrow's lecture. There is one more condition possible in this case, that it is not necessary that all of these cells must have same EMF and same resistance. Like they can have different EMF like E1, E2, E3 and E4, right, and different resistance also like R1, R2, R3 and R4 also. Then what will be the current in the circuit? I will discuss this topic also in the tomorrow's lecture. Please revise them once and try to solve some numerical from it so that you will understand it better, because you will understand any concept better when you solve problem related to that concept, right? So till then class, thank you so much.